Well, good evening, everybody. Welcome to the RSES Technical Webinar Series for RSES members. I'm Mark Lowry, the RSES Executive Vice President. I'd like to welcome everybody to tonight's session on defrost systems for commercial refrigeration, presented by Joe Marchese, CMS. Before we get started, I'd like to thank Keep Right Refrigeration for sponsoring tonight's session. Their generous support is how we're going to keep these webinars at no cost for members, and we value their shared commitment to educating HVACR professionals. Just a reminder, or if this is your first Tech RSES webinar, we launched this series back in May to provide members with additional value for their membership dollar. Much like the RSES Journal, periodic technical bulletins or SAM chapters, and the online archives for both of these publications, these webinars are geared to help you with technical information you can go apply on the job tomorrow. We're generally planning to hold these webinars the fourth Wednesday of every month. Upcoming topics: in July, we're going to have a session on air conditioning compressor troubleshooting. In August, we're going to have using the pH diagram as a service tool. And in September, we're going to have an airflow fundamentals review. Tonight's presentation, like all the webinars, is being recorded and will be available online for viewing in the next couple of days. Joe's presentation tonight will last about 45 minutes, and afterwards there will be a Q&A session. Because we've got so many attendees, we're going to ask you to submit questions using the GoToWebinar dialog box on the right-hand side of your screen, and I'll go through those questions, field them, and ask them aloud to Joe, and then he'll respond, and everybody will be able to hear his answers. Be sure to participate during the presentation to the poll questions that will pop up, and then please take a few minutes tomorrow to respond to our brief survey regarding the session tonight. We want these events to be as useful as possible for you, and the survey is a tool to let us know what you think. Again, thank you very much to Keep Right Refrigeration for sponsoring tonight's session. And now, Joe Marchese.
All right, welcome everybody to this presentation on commercial defrost systems. We're going to cover as much information as we can in the next 45 minutes to give you a good overview on how defrost systems are designed to operate and how to troubleshoot them in the commercial refrigeration world. So let's go ahead and get started. So first of all, why do we need the defrost evaporators? If you work on air conditioning systems traditionally, you'll notice that air conditioning systems don't generally require a defrost cycle. But in commercial refrigeration, that is not true. Those systems, the design of those systems do require some means, some method of defrosting their evaporators on a regular basis. And that's simply because these evaporators that are used on commercial refrigeration systems operate at temperatures below 32 degrees and below the dew point temperature of the air entering the coil. So because of these airflow characteristics of the air coming into the coil, frost is going to naturally accumulate on this coil, and you have to deal with it. It's a necessary evil that has to be controlled, has to be regulated. Too much frost on the coil is not a good thing, but you don't want to go crazy with defrosting too. You don't want to have to defrost the system every 2 minutes. So you have to be able to manage the defrosting of these evaporators in a common sense approach. So if you don't defrost the evaporators, what will eventually happen is the frost will build up on the coils in excess, and now this excess frost is going to cause the heat transfer characteristics of the coil to be diminished, and you'll see your box temperatures rising slowly at first, and then eventually they'll rise to critical points. So yeah, you have to be able to control the defrost or the amount of frost on any evaporator coil. Now, there are many different ways to go about defrosting a coil. The industry has many different methods. We're going to focus on the two most popular methods used today. But there are some systems that use a manual removal of frost, and it's a simple manual method where on a time schedule you have to shut the unit down manually and remove the ice. Your little home chest freezers or your some older commercial chest freezers work that way, where there is no defrost cycle. It's a manual method. Kind of antiquated, but it's out there. So We're not going to talk about the manual method tonight because there's nothing to it, but it's a system that you will come across. Other systems use a timed defrost method where they just shut the unit down and let it naturally defrost every so often. They use a time clock or somehow to just shut the unit down, or somebody manually just shuts the unit off and let it defrost overnight. So there are some systems out there where the manufactured or engineered defrost method is just shutting the unit down and emptying the product out of the case maybe, or just leaving the product in the case for a while and just shutting it down for an hour or two. So that's another method out there, and again, we're not going to cover that method, but we will talk about this method down here, the off-cycle defrost method. Real popular method on defrosting medium temperature refrigerators, the typical system that you would see in a restaurant or a bar or food service. Your typical medium temp cooler, it's going to have more than likely use some type of off-cycle defrost. And then when you get into your low temperature world, when you get into your freezers, your walk-in freezers, reach-in freezers, it's going to use some type of supplemental defrost. Supplemental heat, some type of extra heat is going to be added to the coil on a regular basis and defrost the coil in that method. So tonight we're going to talk about these two popular methods. We're going to talk about the off-cycle defrost technology, and then we're going to concentrate on the electric defrost system used for the supplemental methods. The electric defrost is pretty popular when it comes to your standard low temperature walk-in freezer, reach-in freezer. So we're going to concentrate on these two types of defrost systems. But before we get started on the technical, let me give you some real-world advice for the service guys out there among us. Be very careful when you come to having to remove frost or ice from an evaporator coil. It's part of your job. You're going to come across a refrigeration system that there's going to be a tremendous amount of ice built up because the defrost system is not working. The defrost system is not doing its job. You'll get there. It's an easy problem to realize. You'll just see this cake of ice and frost on the coil, and you're going to have to figure out why that's developing. But one of the things you're definitely going to have to do is get rid of that ice and frost manually. Before you leave that job site, you're going to have to maybe go in and do some manually defrosting of yourself. And let's give you some real-world advice here. Don't go crazy when it comes to defrosting these coils. Do not take a hammer or a chisel to chisel away. Don't take a screwdriver to break away the ice. It's very, very easy. We've all done it. A lot of technicians have made this mistake, unfortunately, including myself, where we've rushed the process of defrosting some of these coils, got a little bit too aggressive, and nicked the coil enough where the refrigerant started to leak out of the coil. And that's one thing you want to avoid by all means. When and if you have to defrost a coil, be diligent, be safe, but don't go crazy with a hammer or a chisel or a knife. Don't scrape the ice off. Don't chip the ice away. Best approach is with a heat gun. A heat gun works very well. Just be careful about the surrounding plastic components. The heat gun could be pretty, could cause some damage to any of this plastic molding or plastic framework around the evaporator. So be careful with a heat gun, but it is much better than using a chisel. It's much better than using a hammer. Avoid using a torch. A torch is not recommended to defrosting an evaporator. It's not a controlled heat source. It will cause you more problems than good. A heat gun generally works pretty well. If you can, depending on where your evaporator is located, another good source is water. If you can take a garden hose to the evaporator and use just plain water to defrost the coil, that works very well. The only problem with it is, depending on where the evaporator is, you may not be able to do that. The evaporator may not be in a location where the water could be safely drained away. So using water is not always a practical means, but there are some coolers out there, there are some freezers out there where that is a possibility. So if you can do it, water works great, but a heat gun generally is a pretty pretty safe way of defrosting coils. So let's talk about the off-cycle defrost method. It is a very popular method on your standard reach-in coolers, your walk-in coolers, your medium temperature, 35, 40 degree boxes. Very popular method of defrosting the coil. This method is only going to be used on systems where your case temperature will not go below 35 degrees. And you'll see why that is in a couple seconds here. But if you have a design that is operating below 35 degrees, you're generally not going to see this method being used. The basic premise here for this method is simple. The control system, whatever's controlling this unit, when the unit shuts off, whether it be on a pressure control or a temperature control, whatever method is being used for control, that control will not allow the compressor to cycle back on until the coil temperature gets above a certain value, which ensures that the evaporator has completely defrosted. So basically, this off-cycle defrost, the name says it all. Every time you go to an off cycle, the evaporator will be defrosted, and the cooling system, the compressor, will not be cycled back on. If everything is working right, the compressor will not be cycled back on until the coil temperature reaches a value where we know that there is no frost left on that coil. So because we're using the control to monitor the coil temperature, we have to make sure that the coil temperature monitoring is proper, and we're going to talk about how that is done basically using either a temperature control or pressure control. Whatever method you're using, whether it's a pressure control or temperature control, you got to make sure the cut-in value, the turn-on value of that controller is high enough to make sure the coil defrosts every time it cycles off. Now, we can use that method of monitoring coil temperature to both control the defrost and also control the case temperature. Medium temperature refrigeration systems, or most refrigeration systems, are designed around a relationship between coil temperature and case temperature. The design of the case, it's designed around a specific temperature relationship between coil temperature and case temperature. And that constant coil to case temperature relationship, we're going to use that to our advantage. We're going to be able to monitor coil temperature, maintain coil temperature, controlled by the coil temperature, but yet give us our desired results of keeping the case temperature where we want it. Generally speaking, walk-in coolers or walk-in units will generally have a 10-degree temperature difference between coil temperature and case temperature. So if my coil is at 25 degrees, if everything is working right, my case temperature should be, or my return air temperature will be around 35 degrees. On reach-ins, they use a slightly different relationship. On a reach-in system, we're looking at about a 20-degree TD. So on our reach-in cooler, medium temperature reach-in cooler, we're looking at a 20-degree difference in temperature between coil temperature and case temperature. So as the picture shows here, as my case temperature drops, as my coil temperature drops, so does my case temperature. And I can control my entire system operation by just simply monitoring coil temperature. When my coil temperature gets down to a low level, that will equate to a low level in my case temperature, and I cycle the unit off. Now on the off cycle, that relationship is not there because that relationship only exists on a running system. So when the system cycles off, your coil temperature is going to rise at a very rapid rate compared to your case temperature. But at some point in time, they will meet each other. And typically, they're going to meet each other at your cut-in or turn-on point. And that turn-on point is going to be the point where, A, the case temperature is not going to be too high, and your coil temperature has elevated to a point where we know there is no ice or frost remaining on the coil. So here's just an example of an operating system. If we start off with a case temperature where at 40 degrees we turn on the unit, and we're actually really trying to get on by about a 20 degree coil temperature. As the case drops in temperature, my coil temperature will drop. When I get down to about 15 degrees in coil temperature, that will equate to about a 35 degree case temperature. The system cycles off, and then my coil temperature rises up. During this process, the coil gets warmer and warmer and warmer. When it gets to 40 degrees or 38 degrees, whatever the magic number is, my temperature sensor or my pressure sensor is going to turn the unit back on, and the unit will come back on into a refrigerating mode. So one of the two methods used to control temperature using this method is a temperature control. We can use temperature or pressure. One popular method is using a temperature control. And you need to think of this temperature control a little bit differently than you would think about a standard temperature controller, because it's not an air sensing temperature control. It's a coil sensing control, and it's designed to sense coil temperature. And one of the common mistakes made in the field today is if this controller fails, somebody replaces it, not knowing or not remembering that it's a coil temperature sensor. They put in an air sensing thermostat, and now the system may work for a little while, but since you're not measuring coil temperature, you're measuring air temperature, and you're not getting a good defrost every time the unit cycles off, because the unit will be cycling off based on air temperature in lieu of coil temperature. So rule number one when it comes to these types of defrosting systems, the temperature control is special. It's called a constant cut-in control, not a constant differential. Constant differential would typically be an air sensing type control. We don't want to use that. We want to use a constant cut-in control, where the cut-in temperature is fixed. When you adjust your temperature in the case, you're not adjusting the cut-in point, because that is fixed by the design of the control. You're going to adjust the cutout point. So on a constant cut-in temperature control, the adjustment is on how the unit cycles off, but it's going to be fixed because it has a fixed cut-in point, and it's fixed because we want to make sure the case temperature always the coil always gets defrosted sufficiently on every time the unit cycles off. Now, since it's a coil sensing thermostat, it has to be inserted or touching the coil. Most evaporators will have a well that this capillary tube, the sensing tube, is inserted into. You have to make sure that when you replace these controls, that sensing tube, that sensing element goes back into the well. If you get lazy and don't put it back in, it defeats the purpose of the design. And sometimes it's difficult. Sometimes where this well is located on the coil is not in a very convenient location, and sometimes it's a little bit difficult to find it, or not find it, but get to it. But you got to take the time, because the system is designed for the sensing element to be inserted into the coil. So make sure you get it into the coil and not just laying on the coil or next to the coil. It has to be into the coil because it has to sense the coil temperature. So two rules. One is when you replace these temperature controls, make sure you purchase a constant cut-in, and make sure when you replace it, you put the sensing element back where it goes. No shortcuts. It's got to go in the well itself. Normally, the cut-in value is going to be around 38 degrees, maybe a little bit higher than 38 degrees. That's going to be a manufactured number, engineered number based on the manufacturer of that unit. It's best typically to use the OEM thermostat when you replace it. When it comes to changing out this control, safe bet is to use the OEM, but you don't have to. They do make universal constant cut-in controls. So you can get a universal control that will work as long as two things, as long as the cut-in value matches the original cut-in value. And then the cutout value, make sure the range on the cutout side is similar to the cutout range of the old control or the original control. So the cut-in value has to be pretty much dead on or close to being dead on. The cutout range, because it's an adjustable range, that has to be close to make this unit work properly. Now the other way of working this off-cycle defrost system is using a pressure control. And it's pretty similar in the approach. But now we're going to use a different control to control the operation of the system. It's not going to be temperature-based. Using a temperature control, we're going to use pressure. And since the evaporator coil has saturated refrigerant inside and the refrigerant is boiling off at a saturation temperature, if you know the pressure, you know the temperature. So we're going to use pressure as a temperature measurement. We're going to measure pressure. We're going to measure the pressure. We're going to control by pressure, and that pressure is going to relate to a specific coil temperature, and that coil temperature is going to relate to a specific case temperature. So we're kind of doing it in two steps in this case. I'm using a pressure control in lieu of a temperature control, but I'm still looking at coil temperature. That hasn't changed. And that coil temperature still relates to case temperature. That hasn't changed. The only difference here now is I'm using pressure as my control means. So these pressure controls have two settings on them. The first setting you want to adjust or need to adjust is the cut-in setting. And that cut-in setting is going to be the pressure equal to the highest coil/box temperature that you want to achieve for your design. So your cut-in pressure, cut-in point of this pressure control is going to be that magic pressure value that relates to a coil temperature, that relates to a case temperature, that will be the highest achieved for the box design. And that's going to also ensure that you get a good defrost. The other side, the other adjustment is going to be what's called a differential adjustment. It's going to give you the ability to select the point where the unit cycles off. The cutout point on this type of pressure control is not directly set. You have to set a differential setting that equates to cutout. The magic formula is right here. Whatever you set your cut-in for, you subtract what you want the cutout to be. You pick the magic cutout point, and the difference between cut-in and cutout is differential. And that's what you're setting on the control. You're setting the differential, the difference between cut-in and cut-out on this pressure control. So for example, if I'm working on a system where I want my cut-in value to be 38 pounds, that's going to give me my right coil temperature to cycle the unit back on. And I want it to cycle off at 20 pounds. Well, the difference between those two is 18, and 18 is going to be my differential setting. So I will set my control with a differential value of 18 pounds. Now, sometimes you have to adjust for long lines, long suction lines. Most of the time, the pressure reading is taken at the inlet or close to the inlet of the compressor. And if your suction line is far enough away from the coil, there's going to be a pressure difference between your coil temperature and the point of measurement down here. So your evaporating pressure here is not going to be the same as the evaporating pressure here if you have a pretty nice size suction line. So you have to adjust, and we're going to talk about the magic number to use for an adjustment to compensate for a pressure drop from the evaporator coil to the point of measurement, which is going to be close to the inlet of the compressor. There are some pressure controls out there, not a lot, but there are some out there that do allow you to adjust the cutout value directly. So keep a watch for that. They always allow you to set the cut-in directly, but there are some out there that allow you to adjust the cutout directly as well. So they're not always using differential, but the majority are. The majority the majority of the controllers used out there do use differential. But watch out, look before you leap. Look at the control, make sure it doesn't say cutout, and it does truly say differential before you start adjusting it. So let's walk through the process of setting up one of these pressure controls. So let's say I have a walk-in cooler, and I know that design of that walk-in cooler has a 10-degree temperature difference between case temperature and coil temperature. And I know that unit is using 134A as its refrigerant, and somebody tells me, or the customer or I decide, that I want to regulate the temperature in that box between a value of 35 and 40 degrees. So 40 degrees is going to be my cut-in point, and 35 is going to be where I want to cycle this unit off to maintain this 5-degree temperature difference in case temperature. So first things first, I'm going to set my cut-in. I'm going to go to my PT chart, and I'm going to look for 134A. I'm going to find what's the pressure value for 40 degrees, because 40 degrees is going to be my higher case temperature. It's going to be it's also going to make sure that the evaporator defrosts properly. If my coil gets to 40 degrees and my case is at 40 degrees, I'm pretty certain that there is no frost on that evaporator. So a 40-degree cut-in value ensures me that there is no frost on the coil. So I just go to my PT card. I find that 40 degrees equates to a 35-pound evaporating or saturation pressure. So I'm going to set my cutout at 35. You always set your cutout first. When you set up these pressure controls, it's always best to set the cutout value first before you play with the differential. Next is I have to figure out or calculate what I want my cutout to be. So if I look at my box design, I want my box temperature to go down to 35 degrees before it cycles off. I know there's a 10-degree difference. By design, I should be cutting off my coil, cutting off my system when my coil temperature gets to 25 degrees. Now, if I do not assume any pressure drop, and let's, for this example, not assume that there's any pressure drop, that the measured pressure where my control is measuring the pressure is the same as the evaporating pressure. So with that assumption in mind, if I know my coil temperature is 25 degrees, I look at my PT chart again, and I know my cutout value should be 22 pounds. I take 35 pounds as my cut-in value minus 22 pounds as my cutout value, and my differential setting is going to be 13 pounds. So for this application, a cut-in point of 35 with a differential of 13 would give you my desired results. Now, if I did have a long suction line, or if I wanted to design in a pressure drop, the normal value that they use, an engineered value, it's not, can't say it's a practical value to use. Sometimes it's off based on the how the unit was piped, but an engineered value would be 2-degree change in saturation temperature. So when we go to the next example, I'll show you how to factor in this 2-degree change in saturation temperature to equate or to factor in a pressure drop or a pressure loss. Now notice I was talking in terms of temperature, not necessarily in pressure drop in terms of pounds per square inch. Most piping charts, most piping manuals, when they talk about pressure drop, they use the term change in saturation temperature. And they use this change in saturation temperature as the measurement of pressure drop. It equates to actual pressure, and we'll show you how that comes to be in a second, but the manuals sometimes call out the 2-degree change in saturation temperature as the guideline. So let's use another example, and this time, this example, we're going to say the suction line is long. We're going to factor in the pressure drop. So now we're going to use the same walk-in cooler. I'm going to change the refrigerant on you. I'm going to use 22. And yes, they do use R22 for some medium temperature applications. It's not 100% popular, but it's out there. So 22 is a refrigerant that can be used for medium temperature systems. And this time I'm going to change the case temperature range. I'm going to say 43 max, 38 min. That's going to be my range. So the cut-in is easy to calculate. Since 43 is my magic cut-in temperature, I go to the PT card, figure out that it's 73 degrees. 73 degrees is going to be my cut-in value. No problem there. Now, let's look at cut out. So I got my 10-degree differential. 38 is going to be my lowest box temperature. That's what I want to try to design to. I'm going to take my 10 degrees away from that. So my coil temperature now, my desired coil temperature is going to be 28 degrees. Now I'm going to subtract 2 more degrees away from that to account for pressure drop. I'm going to use this 2-degree change in saturation temperature as my change in pressure. So I'm going to take 2 degrees away from that value. And that's going to equate to a 26-degree saturation temperature at the point where I'm measuring pressure. Now, I look on my PT card and I see what 26 degrees gets me as far as pressure. In this case, it's 50 degrees. And I simply take the 73 pounds cut in minus my cut out of 50 equates to 23 psi as far as a differential setting. So in this example, by the book, the engineered method would be a cut-in value of 73 and a differential setting of 23. And that would give you my a good cut-in, cut-out range, and also ensure that I get a good off-cycle defrost every time the unit cycles off. So let's throw a hiccup at you. And one of the hiccups we're going to throw at you is blends. Everything we've talked up until this point is with the assumption that the refrigerant inside the evaporator is boiling off at a consistent temperature. And if you stay away from the blends, you stay with the single component refrigerants, that will be true. You know, 22 and 134A, those are all single component refrigerants, not blended, and they do have a constant, consistent pressure-temperature relationship during the evaporating phase. However, with blends, since the blend is a mixture of refrigerants mixed together to work, they do not exhibit that same characteristics. Blended refrigerants, as they evaporate in the evaporator, it's not a consistent temperature relationship. There's the temperature changes as well as the refrigerant is boiling off, the temperature changes slightly. So how do you deal with that? Well, here's how we're going to deal with it. Blended refrigerants have 2 saturation conditions that are used. One is called dew point, and one is called bubble point. The dew point temperature, or the dew point pressure, is going to be the pressure-temperature relationship when the refrigerant is mostly in a vapor state. When your refrigerant is 99.9999999% vapor and a little bit of liquid maybe, we're going to refer to that as the dew point pressure-temperature value. The bubble point, if you look on a PT card and it shows you bubble point is going to be when you have the majority liquid, 99.9999% liquid and a little bit of vapor maybe, just to make it in a saturated state. And that's going to be referred as the bubble point. So what we're going to do is we're going to use the dew point temperature value for my cut-in. That's going to make the system cut in at a good value. It's not a perfect world, but it's going to be better than using bubble point. So when you look up your pressure equating to a temperature that you want to cut in at, use dew point temperature for the cut-in value. Now the cutout, that's a little tricky. The cutout value, what they recommend now for the cutout value is to use the average between bubble and dew point. Some charts do show this average condition. So if you look at some charts, like this example here, it'll show you that at 28 psi, 409A, which is a blended refrigerant, it shows you the average coil temperature right here. It shows you the saturated liquid, which would be the bubble point. This would be your dew point, and this would be the average. So if you have a PT card for the refrigerant you're working with that has the average, then you would want to use the average value for cutout. If you don't have a card that shows the average, you can still make it work. This is not a it's not a perfect formula because the change in temperature and pressure is not linear. It's actually, there's a slope to it, but this method will get you close enough, and it's going to get you close enough where you're going to have a good desired results. So to calculate the average temperature, you can approximate it by using your vapor temperature plus your liquid temperature. Take the two temperatures, add them together, divide by 2. That would give you an average temperature. If you're working with pressures, take your vapor pressure, liquid pressure, add them up, divide it by 2, and that's going to give you your average. It's not an exact number, it's not perfect, but it's going to get you close enough. Again, the change in pressure and temperature is not linear, so this formula is not 100% accurate. But it's reasonably accurate, and for what you're trying to do, it'll get you desired results. So for example, if I was working with 409A, and let's say 20 pounds was the evaporating pressure, and I wanted to calculate the average temperature, I would take 22 minus 8 divided by 2. The average is close to 15 degrees. So let's try to work that into one of these systems. So I'm going to stick with a walk-in cooler. I'm going to stick with the same 10-degree temperature difference. I'm going to use 409A as my refrigerant because it is a blend. I'm going to change the temperature range a little bit on you. We're going to go 41 to 36. So I'm going to look on my PT card. I want to see what my pressure is at 41 degrees. Using the vapor pressure, I'm going to find that it's 35 pounds. So my cut-in value is going to be 35 pounds based on my vapor pressure or dew point pressure. My cutout, all right, the temperature relationship is not going to change on me here. So I'm going to take my lowest box temperature, 36, minus the 10 degrees. And I want to try to cut out this coil at about 26 degrees. That's what I'm trying to do. So I got to find out what's the pressure at 26 degrees. If I use the average, I'm going to find, in this case, it's 28 pounds per square inch. And that's what I'm getting coming up here. Here's my desired coil temperature, 26. That's what I'm trying to get to. If I look on the chart, it shows me 28. Then I just simply subtract the two from each other and find out my differential is 7 psi, which is kind of low, but that's what the engineered value would be. It's not perfect, but it gets you close. So let me show you, give you a real good practical method of setting up these pressure controls without necessarily not having to do all this math. And sometimes these engineered values are off a little bit because of the way your compressor is piping. Maybe your pressure drop is not a 2-degree change in temperature. Maybe you have a higher pressure drop. So you have to factor that in, and that's going to mess things up on you. So a lot of times when you try to set up these pressure controls using the engineered method, it may not give you the best results. So let me show you, let's talk about a good practical way of setting up these pressure controls that you don't have to do the math, and it will be dead on accurate because you're going to set it up for the system that you're working on. So first things first, we're going to set your cut-in, and that is always going to be the same. You have to adjust the cut-in to where you want the system to cycle on, and that's not difficult to factor out. Let me give you some warnings. These scales here that are used, not very accurate all the time when it comes to adjusting the exact cut-in. So I would double-check these scales by attaching your own pressure gauge to the system and watching at what pressure it cuts in at, not based on what the scale says, but with your pressure gauge. So use your pressure gauge as the instrument to set in the cut-in. A lot of times these scales are off. I mean, they're held in place not very securely, and with age or vibration, sometimes they get out of adjustment. So these scales may not give you a good desired cut-in value. So put your pressure gauge on the system as you're setting your cut-in and adjust it by your pressure gauge in lieu of just using the scale on the control. All right, so once you get your pressure cut-in set properly, then go ahead and take your differential value and set it high. Give it a value of 30. Give it a very high value. And then run the system. Run the system, monitoring the case temperature. And as the case temperature is dropping, you keep watching your pressure, and you'll see your pressure drops as the case temperature drops. When your case gets to your desired cutout point, go to the pressure control, and then slowly, very slowly, back off on the differential and very slowly adjust it until the unit just clicks off. And what you've now just done is you just picked that right differential based on the case temperature, the lowest case temperature that you want to achieve. You didn't use any math. You didn't use any numbers. You did it based on what you have right in front of you. And that factors in everything into one nice little ball. It factors in pressure drop. It factors in maybe your compressor's pumping a little bit differently. Then it's older, so you may have some inefficiencies built into your compressor, so you might have some issues there. It factors all that into the nice little bundle here and allows you to select that cutout value or that differential value that is ideal for your working environment. So let me go over that again. Set your cut-in the way you normally would. That's easy. Using a pressure gauge. Set your differential high. Run the system, monitoring the case temperature. When your case temperature gets to the desired case temperature, the lowest case temperature, back off on the differential very slowly. You want to just get that sweet spot where it just clicks off, so be very, very slow and steady. And then when that unit just kicks off, you're done. You've now set the cut-in. That will give you a good off-cycle defrost. It will cut on at the right value, and now you've selected a cutout point that matches the system. Now there is one slight problem with this method. You have to let the system run and monitor it. Sometimes that takes time. So this is a time, not wasting, I shouldn't use wasting, but this is a time-consuming method, but it does make it right. So if you do use this method, I'll give you a little helpful advice. If the box is loaded up with hot product, which chances are it's going to be since the unit is not working and you're there to fix it. If the unit is loaded up with beer or soda or whatever the product is and it's warm or above case temperature that you would want to see it at, take it out. Ask your customer if you can remove the product from the case. You don't necessarily have to remove everything, but remove enough so that it doesn't take that long for the case to drop temperature. If you remove enough product from the case, it's not going to take you that long to drop. But if you have this box that is loaded up with a lot of product, this method will take you a while to achieve. It's a great method, but there is a handicap of waiting. So I hope that will help you on some jobs. It really has helped me on some situations where I couldn't get that calculated cut-in value right. So, Mark, it's time for a poll question.
Okay, Joe. The first poll question we have, everybody, what type of temperature control normally used on a medium temp refrigeration system using the off-cycle defrost method? Encourage everybody to jump in there and select one of those choices, and we'll see how everybody does.
All right. How long do we give them?
We'll give them a minute or two.
Okay.
So far we've got close to 30% of the attendees voting, and they're ratcheting that up pretty quick.
Should I give them the right answer or let them?
Let's wait a couple of minutes or a little bit, and we'll post the results on their own and see how they do.
All right, sounds good. It's an easy question. You guys should get this one right.
Yeah.
I said it a couple of times. I think I said it many times.
Okay, we're coming up on just about a minute here. People are still voting, so we'll let them keep doing it.
All right, sounds good.
I understand some of the people on the East Coast are experiencing the thunderstorms we had last night, so hopefully they'll all be able to maintain connection.
Yeah, we haven't got it here, but I've heard those stories. It's coming.
Good luck. We got about 5 inches in a few hours. All right, I'm going to put up the, all right, so where do I do it? I'm going to close the poll.
Okay.
And then I'm going to share the results. And it looks like 72% of our respondents answered C. Coil sensing constant cut-in.
Constant cut-in, that's the right answer. Yep. Got to make sure the temperature control you use is a constant cut-in. I promise you, if you make that mistake, you will have problems with the operation of that unit. Many guys make that mistake. It's a common error. So keep that in mind when you ask for or replace those temperature controls. Make sure it's a constant cut-in type. All right, we're going to continue on, and we're going to cover the supplemental heat defrost system, and we're going to focus in on the electric defrost. There's the supplemental heat defrost method can be used with hot gas. It could be used with electric heat. We're going to focus in on the electric heat design tonight. It's one of the more popular of the two. The larger systems do use hot gas defrost, but a lot of the smaller walk-ins regions use electric heat, so we're going to cover electric. So now these systems, these supplemental defrost systems, are going to be used on low temperature operations where your evaporating temperatures are well below 29 degrees. It's going to be where you're in a very cold environment where simply shutting the evaporator off on the off cycle is not going to defrost the coil. You have to add heat to the coil to defrost it quickly and efficiently. And one of the things you want to try to achieve is you want to have a quick, efficient defrost. You don't want to leave this unit in defrost too long. You don't want to leave it in defrost too short either. You got to have that perfect combination of a quick, efficient defrost, get the frost away from the coil, melt it away, and then turn the unit back into the refrigeration mode. So again, we're going to cover the electric heat method. And the basic components when it comes to electric heat defrost is going to be just a basic electric resistive heater embedded in the coil. So the evaporator coil is going to be just basically a toaster heater. It's just a traditional heating element, a resistive heating element that very easy to troubleshoot, very easy to work with, but it is definitely embedded into the coil of the evaporator. So don't let me misjudge how important the right heater to use is. The heater has to be sized properly for the evaporator. Even though it's a pretty basic resistive heater, it is designed specifically for the coil. It has the right wattage based on the linear distance being used. It is affixed to the coil in the manner the manufacturer wants or designs. So it's simplistic in how it works, but replacing it, you want to make sure you use the right resistive heater. So you have the heater. You have some type of time clock. There's going to be a time clock that's going to, based on time, bring the unit into a defrost cycle. So the common method here of initiating defrost on these supplemental systems is based on time. It's going to be a time-on defrost cycle. It's going to be time initiated. I'm going to initiate my defrost based on time. And then one popular method of terminating defrost is going to be by temperature. There's going to be a temperature sensor on the coil, and we're going to keep the unit in the defrost cycle. We're going to keep the electric heaters on and melting the ice or frost away from the coil. And when the coil temperature gets to a certain value, we're going to terminate defrost by temperature. So a real common strategy for defrost here is going to be based on a time clock. I'm going to turn on the electric heaters. I'm going to turn off my compressor. I'm going to turn off my fan. Compressor's off, fan is off, heaters are on. I'm going to do that at a time schedule every day. And then I'm going to keep the heaters on until my temperature sensor says my coil temperature is high enough to ensure me all the frost is melted away. And then when my coil temperature gets to a certain value, I terminate defrost and I bring my compressor back on, then I bring my fan back on, and I go back into a normal operating mode. So time initiated, temperature terminated, very popular method, most popular method of defrosting these low temperature walk-in freezers, reach-in freezers. However, it's not the only way possible. If you look down here, there are some systems that use time, where you initiate it by time, but maybe it's terminated based on time. They just keep the defrost heaters on for a fixed period of time. When the time elapses, the unit goes back into refrigeration. So that strategy is time. Not very good because you could either over or under defrost the coil, but you may come across it. The other method possibly used is, again, time initiated, but pressure terminated. Instead of using a temperature sensor, they're going to use a pressure sensor. And then when the evaporating pressure gets to a certain value, they terminate defrost. And that can work because of that pressure-temperature relationship. I know pressure, I know temperature, I can terminate defrost based on a pressure value. So there are some systems out there that use a pressure control to terminate defrost. But by far, the most common method is temperature. Time on, temperature terminated. So here's a typical defrost time clock used. There's several different manufacturers out there, but they all share some common basic features. So one of the basic features are, when do you initiate defrost? You have to have a means of setting your time on or your initiation cycle. Now this common defrost clock shown here uses these pins right there. These pins are going to be placed at the time of day where you want the defrost to come on. When that pin here gets to this time slot right here, it's going to put the unit into a defrost mode. So you can select how many times a day and the interval between defrost you want. This particular time clock allows you to put the unit in defrost every 2 hours if need be. Now that's not realistic, but you select, the technician selects how many times a day you want to put this unit into or initiate a defrost cycle. So it's subject to technician's discretion. Now how do you know? What do you use to judge how many times you want to defrost the unit? Because like I said earlier on in the presentation, you don't want to overdo it. You don't want to have to defrost this coil every 2 minutes. That's a waste of energy. So here's the basic premise that you have to think about when you select how many times a day you want to bring this defrost timer into a defrost cycle. It's going to be based on two very important factors. It's going to be based on the ambient temperature surrounding the box and the infiltration value of the box. So if you're working in a very hot and humid environment, if your box is located where it's very hot, very humid, you may need to go with more defrost cycles per day. If the box is being used a lot, where the door is being opened a lot, and you're bringing in this warm air a lot each time the door is open, that warm humid air is going to eventually condense on the evaporator and have to be defrosted. So if it's a hot and humid environment and they're in and out of this cabinet regularly, you might have to go with several defrost cycles per day. If you're in a dry, cooler environment and the box is more for storage, long-term storage, maybe they're only into it once a day, if that, maybe every other day, then maybe you don't have to go with so many defrost cycles per day. Maybe two, maybe one defrost cycle per day works. Maybe two works. So it's a judgment call on the technician's part based on the environment. Do you go 6 defrosts a day? That's excessive maybe. You know, the average defrost intervals usually anywhere from 2 to 4 times a day. Those are real common choices to use. But some systems may need more than 4. Some may need less than 2. It's a judgment call on the technician's part based on the operating environment where this case is located. In any case, on your defrost clock, you select that time interval. This clock is here. This selection is using these pins. On this electronic version, you have to do it through programming. You have to go into the program and select it by programming. Now, in the center here of this clock is another time wheel, because this is a 24-hour clock. This larger wheel is a 24-hour clock, so it allows you to select, you know, the defrost selection for a 24-hour period. But I also have another clock, another wheel in the middle here with a time value on it. That's going to be my, what they call a fail-safe termination point. If for any reason my typical or my normal termination method does not take me out of defrost, I don't want to leave those electric heaters on forever. That's not a good idea. So as a backup, I'm going to set this dial right here, so that if for any reason my defrost goes to this period of time, whatever that be, 35 minutes or 40 minutes or 50 minutes, if I'm defrost, if I'm in defrost that long, something's wrong. This time wheel here will then terminate defrost based on time. So this is kind of like your backup, where your heaters are on too long, something's wrong, and you want to be safe and shut it down even though your normal termination method is not working. So this is your termination based on time, and typically it's used for backup. Your electrical connections are down here, and this is going to vary. This is just one example for one type of time clock. You're going to see different configurations out there. You're going to have to go to the wiring diagram. Most defrost clocks, on the cover, there's going to be a label that's going to show you the terminals configuration or the wiring diagram. Use this as a reference. Even though this is a common defrost clock and a common terminal configuration, it's not always that way. Always default to the diagram on the timer itself. That is the best, safest, most sure way of knowing what the terminals identify. But these are where you're going to connect your circuitry to control your compressor, your fans, and your heating. If I flip that timer over and look at the back side, I'll show you the time clock. This is a simple time clock, 24-hour wheel that's running all the time. It does have this little window right here, which is a valuable little added feature they put there for technicians. Oh, sorry about that, guys. If you were to flip this over and then safely energize that timer, and be careful when I say safely, these are all live hot terminals here. So if you were to somehow safely, and I'm going to make sure I say safely again, safely somehow get to the point where you can turn this time clock on while it's flipped over, you'll see this little, you'll see the time clock spinning in here. And it's a nice way of identifying that that time clock is working. You can use it as a measurement of seeing if the timer itself is not burnt out inside or if the motor itself is not defective. So it is a nice little indicator. Now early on I talked about, well, let me go back. Here's my connection points right down here. This is going to be where I'm going to switch from my compressor on, and I'm going to switch over to my compressor off and my heaters on. I'm not going to have, on an electric system, an electric defrost system, I'm not going to have my compressor on at the same time I have my heaters on. It's going to be one or the other. Now this defrost clock has this slider right here that will allow me only to make contact between here or here, but not both at the same time. These contacts will either be, one will be open, one will be closed, but never at the same time, unless there's a problem and they're welded together. And that does happen. Sometimes these weld together and they don't switch back and forth. But on a normal operating system, excuse me, only one of the two of these contacts are going to be made, because that's going to allow me to have only my compressor running and not my heaters, or my heaters running and not my compressor. Now what actually controls these contacts is this slider right here. The gears here, the gears behind this time clock, when it goes into a defrost mode, the slider is going to move. And that slider is going to make the contacts for defrost, open the contacts for refrigeration. And then when the timer says terminate, the contacts for refrigeration are going to be made and the heater contacts are going to be broken. And that's all done by the slider here moving back and forth, and the slider is controlled by the gearing behind this time clock. Now when I'm in a defrost mode, since I'm going to terminate it by temperature, not by time, I have to have a temperature means or a different means of moving the slider without using the time clock or the time gears to move the slider. Because normally the slider is moved by the gearing based on time. But what they've done is they've incorporated this termination solenoid into the system. And this termination solenoid is another way of moving the slider back and forth, back to the refrigeration mode. So when I'm in defrost, and my defrost contacts are made and my refrigeration contacts are open, the slider is going to be in a position. If for any means I energize this solenoid coil, if I put current to this coil, voltage to this coil, if I make a circuit to energize this coil being energized mechanically will move the slider and break the heating circuit, make the refrigeration circuit, and put the unit back into refrigeration mode by me energizing this solenoid coil. So that's why they call it a termination solenoid. I energize this solenoid, and now I move the slider back to make the contacts for refrigeration and break it for defrost. The heaters used, the electric heaters are used on these systems are pretty basic. Again, they're designed to give you a clean, efficient, fast defrost. So when it comes to replacing these heaters, go with the OEM. It's best to use the OEM heater because they are designed so many watts per linear foot. So you want to get the wattage right per linear foot. You don't want to have too much heat. You don't want to have too little heat. So you want to make sure their wattage per linear foot is accurate. They're also configured properly. They're all different shapes and sizes to fit nicely in the evaporator coil. So you want to make sure that you get the right fit. You just don't want to use any heater that just lays on the coil. You want to get the heater that fits into the coil properly. So in general, it is best to use the OEM. Now there are companies out there that make replacement heaters. You give them the specs and they will make it to size for you. So there are companies out there that will do that, but that's a process because you have to send them the specs and the size and the shape and everything, and then they'll make it for you. It might just be easier to go to the OEM and just order the original. But when you do it, make sure you get the right heater because you don't want to over or under defrost the system. So let's look at a common circuit. This is not the only way it's done. There are several different circuits being used out there. You have to look at the wiring diagram to see the one that you're working on. But this circuit here that I'm going to show you now is pretty common. It's a pretty common method of how the time clock, this is showing you how the time clock is connected to the system and how it controls the defrost. The time clock is really the brains of the defrost cycle. It controls when it comes on. It's part of the defrost termination. It's the heart of the defrost system. So knowing how the time clock interfaces with all the other components is pretty important. So we're going to show you this step by step. Now there is another component that makes the temperature termination part of this method work, and that is this termination thermostat, or this single pole double throw thermostat. This is also a critical part to the design of how these units are terminated. Time clock initiates the defrost, turns it in, but the way I energize this termination solenoid, here's my schematic symbol for this termination solenoid. The way this solenoid is energized is through making a contact within this temperature switch here. That's how I am able to use temperature to terminate my defrost. When this switch closes, when the right two contacts make in this switch, it's going to energize this termination solenoid. It's going to get me out of defrost. I'm also going to use this switch, same switch, since it is a single pole double throw switch. I'm also going to use that to turn my fans back on after defrost. And this is an important feature or design of these electric defrost systems. Once I terminate defrost, I do not want my fans coming back on immediately. And the idea behind that, or the reason behind that, is the coil is hot and wet because I've just melted away some of this frost, and it's going to be hot and wet. I don't want to blow that moisture or that hot air into my case. So the design of the system is going to purposely hold off the fans from coming on. After termination, my compressor is going to come on, and I'm going to keep my compressor on, hold my fan off until my coil temperature drops. When my coil temperature drops, and usually the magic number is about 25 degrees. Some systems it's 20, but between 20 and 25 degrees, when my coil temperature gets to between 20 and 25 degrees, I'm going to allow my fans to come back on, but not before my coil drops to that temperature. And that will prevent hot, warm, moist air from blowing into a cavity. So when you look at a defrost system and you see the termination occur, you should notice that the fans are held off. If the fans come on right away, that's not right. Something is wrong. That's one of the things you want to check for when you're looking at this defrost cycle. When you terminate defrost, you want to watch the fans, and you want to make sure the fans do not come on right away, that they're held off a certain period of time and cycle on when the coil gets to about 20 or 25 degrees. So that's an important part of the overall design, is holding off the fans after the termination of the defrost heaters. So let's look at a common circuit. We're going to start off with the unit being in refrigeration mode. So when I'm in refrigeration, I'm going to make the contacts here on number 4. I'm going to go through my temperature switch for the system, and my compressor is going to be energized. So line voltage is going to be applied to terminal 3 right here, or this bar here, and then I'm going to make the circuit through these contacts through my regular temperature control to my compressor, let's say. And then I complete the circuit back through the X terminal back to the other side of line voltage. At the same time, my fan will be on. Now I'm going to assume that my coil temperature is sufficient, so my fan should be running. But do notice that the fan circuit does go through this switch right here. And this switch has to make to complete the circuit for the fans to come on. And notice that that circuit is on the other side of line voltage. Here's your one side of line voltage that feeds the fan. The other side is feeding the compressor. But the brake for the fan on this temperature switch here is on the opposite side of line voltage. And they do that specifically. They do that on purpose. And you'll see why coming up. So now we have a operating system. My compressor will cycle on and off based on temperature, and my fan is running all the time. Now the time clock is going to run, and when this pin here gets to here, then I'm going to switch over. This slider bar in the back is going to switch. It's going to close this contact. It's going to open up these two contacts. So let's do that. So I'm going to go into defrost. I'm going to shut off, open up these 2 points. I'm going to close this point here, and my heaters are going to be on. So now I have my heating circuit complete. My fan is off. My compressor's off. My electric heaters are on, defrosting away, melting the frost and ice away. After a couple minutes, 5 minutes, 10 minutes, whatever that magic number is, I want to terminate the defrost. And I'm not going to do it by time now. I want to do it by temperature. This temperature switch right here, when I get to about 55 degrees, 55 degrees is the magic number usually. That's what's normally used. So when my coil temperature gets to 55 degrees, this switch right here is going to make. And that's going to complete a circuit to this termination relay, solenoid, termination solenoid. And that solenoid is going to get me back into refrigeration. So let's show you that in operation. So I got to put voltage to this switch right here to cause these sliders to move, to break the heating circuit and make the refrigeration circuit. So when that switch makes, that solenoid is energized. When that solenoid is energized, it shuts the heaters off and it brings on my compressor. Now my compressor's running, but my fans are not, because this switch here, right, the coil temperature is 55 degrees, so my coil is warm, it's hot, well not hot, but warm. So I'm not making that circuit back to my fans. Even though this contact here is made, my fans will not be on because this switch here is open. As soon as my coil temperature drops, I'm going to open up this switch, and now this switch here will make, this part of this single pole double throw switch makes, and now my fans will come on. Now I complete the circuit, and that switch closure occurs at about 25 degrees, so now my fans come on without blowing hot, warm, humid air into the case. That's because that's what you don't want to do. And now I'm back into my normal refrigeration cycle, where my fans are running, my compressor's running, and I just melted away all the frost on that coil and didn't allow it to accumulate to a dangerous high level. Sometimes they also put on a second temperature safety switch. There'll be a second switch on the coil. So if you see two switches, two temperature sensors on the coil, a lot of times the second sensor is going to be a safety sensor, so that the coil temperature gets too high, it shuts the heaters off without the heaters melting anything. You don't want the heaters being on without too long and making that coil get hotter and hotter and hotter. So sometimes you also see a safety thermostat incorporated into the design, and that's just a backup in case the heaters get too hot. It opens up the heating circuit. Sometimes this switch right here, let me go back to my very first slide here. This switch right here will be two switches, not one. This single pole double throw switch may not always be that. It may be one switch for termination and a separate switch for fan delay. But most commonly, it's a single pole double throw switch where it's two switches in one body. That's the most common. A lot of guys refer to that as a three-wire thermostat. Three-wire thermostat, real common way of doing it on a electric defrost system. But not always. There are some times where these two switches are split into two. So let me scroll back through here real quick. And I think, Mark, it's time for a poll question.
Okay, Joe. Let's see. You
there, Mark?
Yep.
Okay.
I'm here. Launch that second question. The defrost cycle of a walk-in freezer can be terminated by time, temperature, pressure, or all of these? Even though we're running a little bit over here, still got most everybody on the call still, so hopefully they can all
we're finishing up. Yeah, we'll finish up after this poll question, and we'll be ready to answer some questions.
Yeah,
sorry for going a little bit. I apologize for going late. There's just some good information I wanted to get out.
Absolutely, and at least one member is very happy because you got him out of mowing the lawn.
You're welcome. Hey, that's the way to market these webinars.
Absolutely.
You know, you get away from the honey-do list.
There you go. I'm learning. All right. Looks like our participation is starting to slow down, so we're going to close the poll. We've got 80% of the attendees participating, and of that, 95% of the attendees said all of those options are how the defrost cycle can be terminated.
That is correct. Absolutely. Yep, that is true. All of them can be used. Temperature is the most popular by any means, but you can come across any of the three methods.
Okay.
All right. Am I have control again?
Yep.
Okay. So let me just go over some little small troubleshooting tidbits, and then we'll open it up for some questions. So when it comes to troubleshooting, it's very easy to break it down into one of two problems. Either you're over defrosting or under defrosting the evaporator. Under defrosting, by all means, is the most common problem. And you can easily identify under defrosting by a iced over frozen evaporator, easy to identify. Over defrosting, not always easy to identify, but some common things to look for for over defrosting is little ice pellets right on the ceiling on the top of the walk-in freezer, right close to the discharge of this fan. If you see these little ice pellets on the top, not always, but a lot of times it means that your fan may have been coming on too quickly after the termination cycle, and you're blowing some warm, humid air into the case, and these little icicles or little ice droplets are forming on top of the walk-in freezer, and that's not what you want occurring. So one thing to look at when you're looking at problems is to look at the ceiling right by the discharge of the evap. So let's talk about under defrosting. That's the most common. When it comes to troubleshooting, you treat it like a electric heating circuit, right? Most common way of testing the system is to manually put it into defrost. Turn this knob, turn it counterclockwise till it clicks into defrost. Take an ammeter, clamp it onto the defrost leg, whatever circuit is being used right here. So this leg right here, clamp your ammeter on there and see if the heaters are drawing current. If you switch it manually into defrost and your ammeter says that the heaters are drawing current, chances are that the heaters are not your problem, that the heaters are not defective, but for some reason the unit didn't go into defrost. So more likely the defrost clock didn't get you into defrost. If you switch it into, manually put it into defrost, and you clamp onto your electric heating circuit and you have no amperage draw, then I'd be looking at my heating circuit. Something opened in my heater. Maybe I have an open heater, maybe I have a broken wire or something. So divide and conquer. First step is to divide and conquer. Manually put it into defrost, measure, see what you get. If you realize that the heaters are working and it's a time clock issue, and that's not uncommon, leave it in defrost. Monitor the defrost cycle. You initiated it by manually. Now you want to see if the defrost clock or the defrost system takes it out of defrost normally. So you just wait. You know, you monitor your amperage draw, and you want to see how long it stays in defrost. If it stays in defrost based on time, in other words, you look at your termination time here, and if you're noticing that it stays in defrost and then terminates after this time period, then my termination switch is screwed up, maybe. Or if it never comes out of defrost, it just stays in defrost, maybe you have a combination of problems. So you kind of put it in defrost and you kind of see what's going on, and that'll help you kind of get to where the problem may lie. Because you know that it should, at one time, energize this coil and terminate defrost. If that never occurs, that may be a problem for you. Sometimes what techs will do is once they terminate defrost, they kind of get through a defrost cycle, and sometimes they don't know if the time clock is working here. They'll put a little mark right here. They'll take a little Sharpie, put it here, and then they'll just let it run for an hour, come back, and if they don't see this mark move off of this pointer, then they know this time clock is dead. So they'll just change the time clock out, and that will tell them that it never went into defrost. It never went into a defrost cycle. So, you know, putting a little mark here, or just kind of remembering where you left it, go have lunch, and then come back and then see where you're at. If the time clock has not moved, then the time clock is bad. So you check the time clock out by just visual inspection. If you flip it over, you can look at this little window here, excuse me, to see if the window is being made. You can also look at the contacts. For whatever reason, it's not switching back and forth. Maybe the contacts are welded shut. So you can identify some problems by looking at the contacts and seeing if they're welded shut. So not difficult to troubleshoot once you recognize that it's not going into defrost. All right, guys, time for some questions. So Mark, if you want to fire some questions, hopefully I can answer some questions for some guys.
Okay, and we certainly have a lot of them rolling in. They've been coming in throughout your presentation.
Okay.
I've got one here where we're asked, how do you determine heater wattage? And specifically, the member's got a blast freezer operating at -40 Fahrenheit, and he's replacing heaters that are inoperative. There's no data plate on the coil. The only info available is the voltage, operating temp, and coil's physical size. So how would he?
Question.
Okay.
A good question. Well, if you can't, I would initially say go back to the original equipment manufacturer and ask them for their recommendations. In lieu of that, if you can't get it from the equipment manufacturer, I tell you what, I don't have the exact answer in front of me right now, but if you take his email address, I will find out and I will email him back directly.
Okay, we can do that.
Yeah, we can find out best approach, and there is a method to approximate it, but it's eluding my mind right now.
Okay.
But first approach is go to the OEM. But in lieu of that, I'll do some research and I'll get an answer for that member.
Okay. Then the next question is, what values are measured by electronic demand defrost controls to determine defrost needs?
That's an open-ended question because everyone's trying to find that magic pill. They're trying to find what's the best way of determining how to put the unit into defrost other than by time initiation, because time initiation is best guess values. So this demand defrost depends on the manufacturer. Some manufacturers are looking at suction pressure, suction temperature, suction pressure versus temperature versus ambient temperature. That's an OEM definitely spec item. You have to go back to the manufacturer of that control and see what they're looking at. Everyone is trying to find the best method of this for demand defrost, and not everybody's playing by the same rules. So unfortunately, it's a bad. You have to go back to whoever the manufacturer of that product is and see how they're doing it.
Okay.
But it could be by pressure. It could be by pressure and temperature. It's definitely driven by the design engineer.
Okay. The next one is, what happens if your customer puts their air temperature probe into an oil bath?
Air temperature probe. All right, so we shouldn't be using air temperature for these two defrost methods that we've just discussed. But there are some designs out there where they're going to use a timed-off defrost, where the walk-in cooler will use an air-sensing thermostat. So the walk-in cooler is not using a coil-sensing thermostat. They're using an air-sensing thermostat. And then they're going to defrost the coil based on time. There's going to be a time clock in the system, and maybe once a day they're going to shut the cabinet off for about 90 minutes and defrost it once a day for 90 minutes. And then for the rest of the day, they're going to use case temperature to control the operation of the unit. Now, if they're putting the sensing element in an oil bath, then they just using that to the oil temperature is going to equate to case temperature. So they're using an oil temperature bath to equate to case temperature, and they're going to use a different way of defrosting the coil. The coil is going to be defrosted now just by time on, time off, once a day maybe for 90 minutes.
Okay.
And that's a different way of doing it. It's not what we talked about tonight, but it is a different way of defrosting a walk-in cooler.
Okay. And speaking of walk-ins, early on when you were talking about temperature differential between reach-ins and walk-ins, you mentioned that the differential was 10 degrees for one and 20 degrees for the other, and one of the attendees asked why that difference.
Sure, no problem. Good question. The reason for that difference is the basic design of what they're trying to achieve. Walk-in coolers are generally considered long-term storage. So because they're long-term storage, they can design the coil where it's larger and bigger, and they can get a better temperature difference relationship by making the case temperature. Let me back up a second. They can make the evaporating temperature versus case temperature where they're not trying to keep the humidity in the box too high or too low. In long-term storage, in the case of a walk-in cooler, it's considered for long-term storage. That relationship of 10 degrees keeps the humidity value higher, so that you keep the product moister, keeps the product wetter, if you want to use the term wetter. But when you have a 10-degree temperature difference, you keep the relative humidity up in the box higher, and that 10 degrees differential gives you a higher RH value in the box. Now on a reach-in cooler, they sacrifice that for space. Reach-in coolers are considered short-term use products. So because they're short-term use products, they try to get smaller evaporating coil footprints, and that footprint leads to a tighter evaporator coil, and then they sacrifice by having a wider TD. And that sacrifice now gives them a more dehumidification that is occurring in the case, and you tend to, over a period of time, will dry up the product in those reach-in coolers. So that 20-degree differential is a necessary evil to save space within the cabinet, but since it's considered short-term, your RH value in the cabinet is going to be lower, and you'll dry up the product quicker. So by design, they recommend that you don't keep product in the case too long. So the TD is based on RH. If you want the smaller the RH value, the smaller the TD value between coil and case, the higher the RH value is going to be in the case, better for long-term storage. The larger the TD value, the more it dries up the product.
Okay.
That was a long-winded question, sorry.
That's right. Another question came in. Do you recommend the use of a lubricant when inserting the cap tube of the thermostat into the well?
Sure, yes. Yeah, it actually also helps with heat transfer. So if you use a good thermal paste, it actually is a benefit.
Okay. A little bit more involved question. How do two-speed EC, and I'm assuming it means electronically commutated motor, systems affect defrost? Any concerns if the two-speed system is a retrofit?
Well, the only concern I would have was just to make sure that two things. One, determine the fan delay is properly set up so that when you come out of defrost, that motor does not come in, the fan motors don't turn on too quickly. And then the other concern would be when you lower your fan speed, you're going to drop your coil temperature. That's going to give you more of an icing effect, frosting effect. So your initiation time to bring on your defrost cycle may need to be modified so that you bring it on more frequently, because as you lower that fan, you're going to get more of an icing effect on the coil. And as long as you select the right initiation period for that two-speed operation, you should be okay.
Okay. Another question, do manufacturers list the temperature differential for all coils, especially in a supermarket setting where there are different products in cases?
That is a manufacturer's spec item, so yes, they should. Manufacturers should have a rating for their coils based on what they're looking to achieve. So that 10-degree differential, 20-degree differentials, those are pretty consistent values. If it's something other than that, the manufacturer should spec that, or should have specifications on that.
Okay. Can you use pressure control on a system that balances pressures between the high and low side on the off cycle?
No. The pressure control system only works if you have a expansion valve that holds the evaporating pressure in place while it's on during the off cycle. So if you have a cap tube system, pressure control cannot be used.
Okay. Let's see. Trying to scroll through some of these. How many defrost cycles in 24 hours are recommended for a storage freezer operating at -18 centigrade, and what is the defrost time?
All right, so it all depends on the ambient conditions that the box is working in. If it's going to be in a very hot and humid location, and they're going to be in and out of that cabinet a lot during the day, then I would say at least 4 defrosts a day. You might even need to go a little bit more than 4, but I would start off with 4 defrosts a day and then take it from there. If it's in a dry environment, not so hot, not so humid, and the infrequency of going into the cabinets is light, it's kind of more of a long-term storage box, then I would start off with 2 and then maybe back it off to 1 if I can. So it depends more on the ambient condition rather than the evaporating temperature.
Okay. Another question just came in. Are there different procedures for gravity coils?
Yes. Gravity, well, the method for gravity coil is similar. Okay, so you still have your same cut in and cut out pressure values. So you're going to use a pressure control. All right. Just the difference is going to be where you're going to take your temperature measurement. So with the gravity coil, you're going to, it's better to use the alternate method that I was telling you about earlier, where you set your cut in to whatever you want the cut in to be, and then you measure your case temperature and adjust your differential to match the case temperature. That works much better for gravity coils.
Okay. Yet another question. On a medium temp, large walk-in system, would a pump down speed up the defrost?
I guess in theory, yes. I've never heard any numbers claiming that to be a fact or not being a fact, but if you don't have refrigerant in that coil, or you have limited amount of refrigerant in that coil, I would imagine that the coil would get up to temperature quicker than if it was filled with saturated refrigerant. So I would say yes, it would, but I've never heard any facts to back that up with or any literature saying it does. But if you think about it, yeah, it would. It would definitely. It should speed up the defrosting time.
Okay. One more here. Where is the best place to place a defrost termination on electrical heat defrost in a humid environment?
Well, my rule of thumb when it comes to placing sensors on coils is I always defer back to the manufacturer's original location. They've done the testing and they've picked the spot that they feel is the best location for whatever the case may be, whatever type of coil it is or the environment. They tend to have done their research much more than a service guy has. But in general, if you had to pick a location, I would say that top of one of the return bends, top where the refrigerant is coming in. No, I'm sorry, the bottom where the refrigerant is coming into the coil, the bottom section on one of the return bends. It's probably going to be one of the coldest locations, and that's the location that you want to ensure that the coil is defrosted properly before you terminate defrost. So if you had to pick a location by yourself, I would say towards the bottom of the coil at one of the bends at the bottom, in lieu of using wherever the manufacturer has selected.
Okay.
Hopefully that answers that question.
It sounds like it to me.
Okay, good.
I think that is just about all the questions that we've had come in.
So would you be able to get that one member's email address? And
yes, sir.
I'll answer his question.
About the sizing, when he doesn't have all the information?
Yeah, there is a method out there. I just have to find out for him. Okay.
Yep, we will definitely do that. And several people have asked for your email, Joe.
Okay.
I'm not sure if you wanted to post that out there for everybody.
Sure. You want me? You guys ready? I'll give you my email address. If you have a question about tonight's presentation, feel free to send me an email. I may not get back to you right away, depending on how many emails I get, but I will try to get back to you in a timely fashion. So it's Joe. As a matter of fact, I'll type it on the screen for you. You can still see my screen, right, Mark?
Yes, sir.
There you go. Joe@Coltronics.com. So if you have a question outside of this presentation, just send me an email and I'll try to answer it as fast as I can.
Outstanding. Well, I think
Any other questions?
That's all the questions. Let's see. One more just jumped in there. Let me see. Nope, just one of our good friends. Oh, no, here comes one more technical one. In a reach-in freezer with no drain heater from the original manufacturer, what can be done to facilitate drainage?
They do make universal drain heaters. A couple different manufacturers out there have universal heaters that you could use. Some of them lay in the drain pan. Some of them actually can get inserted into the drain line itself. They're small enough where they'll fit in the drain line. So if you go to your wholesale house, you can kind of look around and ask them for their recommendations. But they do make universal little drain heaters that'll fit either in the pan or actually go inside the drain line. I think Supco, if you look at Supco's product line, they may have something that would be a universal fit for you.
Okay. Let's see, and one more came in. What do you think about demand defrost retrofit kits?
If they work, they're great. If they work, they're fantastic, because the idea of determining when to go into defrost based on a physical value rather than having to guess at time intervals is definitely the way they work. I mean, much better. I would do some research to see if the retrofit kit that you're using has been used by others and they had good success with it. You know, everyone can claim to have a good demand defrost system. And I'm not saying that they're not out there. They probably are. Just get some recommendations to make sure that they do what they say they do. But that's definitely the way to go. If you can use a demand defrost system, best approach, because now you're only defrosting when you have to defrost. But not every kit is equally made.
Okay. Well, that does seem to have summed up all of our questions. Several people asked about getting a certificate after the after tonight's session, and we do have everybody's email address, and we will be sending a certificate of attendance to everybody that was here. And that pretty much answers all the questions that we got.
Fantastic. I hope everyone got something from this presentation. Hopefully it was worth their hour and 40 minutes of their time.
Absolutely. I'm sure it was, Joe. We'd like to thank Joe again for being one of our pilot speakers for this webinar series, and like to thank all of you, the attendees, for joining us tonight. And we'd also like to again thank Keep Right for sponsoring tonight's webinar. And be sure to watch your email and the RSES Journal and the RSES HQ News for information on registering for the next one, which will be a month from now on July 24th on air conditioning compressor troubleshooting.
And it's a good speaker. Art is a very good speaker. You guys will like his presentation. So
that's right.
Come back for that one. Yeah, come back for that one. It's a good topic and a good speaker.
Excellent. All right. Thanks a lot, Joe. Thanks, everybody.
All right. Thank you.
Have a good night.
All right. You too.